August 27, 1945. The Pacific Ocean, 500 nautical miles northeast of Tokyo. The war had officially ended 12 days earlier, but the vast expanse of dark water still held secrets that would challenge everything American naval intelligence thought they knew about enemy capabilities. Lieutenant Commander Robert Sellers stood on the bridge of the USS Blue, scanning the horizon through his binoculars as radar operators below deck tracked an enormous contact moving slowly on the surface. The signal was unlike anything they had encountered during 4 years of Pacific warfare. What approached them through the morning haze was not another surrendering destroyer or damaged cruiser limping toward port. The silhouette emerging from the distance defied immediate classification. Too large for any submarine the Americans had encountered, too narrow for a surface warship, too long for anything that should be able to submerge. As the mysterious vessel drew closer, flying the black surrender flag that had become familiar in recent weeks, the crew of the Blue realized we were witnessing something unprecedented in naval warfare. The submarine that surrendered to them that morning measured 400 feet in length, nearly 24 feet longer than their own destroyer. Its beam stretched 39 feet across, just as wide as the Blue itself. The massive hull displaced over 5,900 tons when submerged, more than double that of the largest American fleet submarines. This was no ordinary undersea vessel that had surfaced to surrender in the final days of the Pacific War. This was something entirely different, something that represented a quantum leap in submarine design and strategic thinking that American naval architects had never imagined possible. The vessel bore the designation I-400, part of what the Japanese called the Sentoku class. As American boarding parties prepared to inspect the surrendered submarine, none of them suspected they were about to discover one of the most ambitious and terrifying weapons programs of the entire war. The I-400 was not simply a large submarine built to sink ships or conduct reconnaissance. It was an underwater aircraft carrier designed to carry death across vast ocean distances to targets that military planners had assumed were completely safe from submarine attack. The discovery began to reveal its true nature as American naval engineers climbed aboard the massive vessel and began their systematic inspection. Forward of the conning tower, they found something that initially puzzled them completely. A large cylindrical structure ran along the submarine's centerline, sealed by enormous hydraulically operated doors. The compartment was empty when they found it, but its purpose became clear as they examined the sophisticated mechanical systems surrounding it. This was an aircraft hangar, designed to store 3 complete military aircraft inside a submarine while submerged hundreds of feet below the ocean surface. The hangar itself measured over 100 feet in length and was completely watertight, sealed by a 51mm rubber gasket that could withstand the tremendous pressures of deep submersion. The access doors opened hydraulically from the inside or manually from the outside, allowing aircraft to be moved from the protected storage compartment to the submarine's deck for launch operations. Adjacent to the hangar, the Americans discovered a complex crane system capable of lifting fully assembled aircraft from the storage compartment and positioning them on a catapult system mounted forward of the conning tower. The catapult system itself represented sophisticated engineering that challenged American assumptions about Japanese technological capabilities. A 26-meter compressed air catapult was built into the submarine's forward deck, capable of launching aircraft to flying speed from a stationary platform. Recovery operations were handled by a collapsible crane system that could be deployed when the submarine surfaced and retracted for diving operations. Every aspect of the aircraft handling system had been designed for rapid deployment and recovery, allowing the submarine to surface, launch its aircraft, and submerge again within the shortest possible time. But the aircraft themselves proved even more remarkable than the systems designed to carry them. The Americans discovered detailed technical documentation for the Aichi M6A1 Seiran, a specialized float plane designed specifically for submarine operations. These were not makeshift adapt, but purposations of existing aircraft, built military planes engineered to fold into impossibly compact configurations for storage inside the submarine's hangar. The Siren could fold its wings back against the fuselage, collapse its horizontal stabilizers completely, and fold down the upper portion of its vertical tail fin. Even the floats that enabled water operations were removable, stored in separate compartments within the submarine. The performance characteristics documented in the captured technical manuals astonished American aviation experts. With floats attached, the Siren could achieve speeds of 295 miles per hour, respectable for any naval aircraft of the period. With floats removed for pure flight operations, the aircraft could reach 348 miles per hour, making it faster than many contemporary fighters. Each Siren carried substantial firepower despite its compact design, armed with either a Type 91 torpedo, two 551-pound bombs, or a single 1,874-pound bomb. A 13mm machine gun provided defensive armament for the radio man position. As American intelligence officers pieced together the captured documentation and interrogated the submarine's crew, the true scope of Japanese strategic thinking became clear. The I-400 was not designed for coastal patrol or anti-shipping operations. It had been built to attack the American mainland itself. Original targeting plans called for strikes against New York City and Washington, D.C., using the submarine's unprecedented range to approach the American coast completely undetected. The vessel carried enough fuel to circumnavigate the globe 1.5 times, giving it the capability to reach any target on Earth without refueling. The strategic implications were staggering. American coastal cities had been considered absolutely safe from direct attack by enemy aircraft. The vast Pacific Ocean provided a barrier that no conventional aircraft could cross, and American naval and air forces controlled the approaches to North American waters. But the I-400 class submarines could have changed that calculus completely. Approaching submerged and undetected to within a few hundred miles of major American cities, these underwater aircraft carriers could have launched surprise attacks against targets that had no warning and minimal defenses. The Panama Canal had emerged as the primary target for I-400 operations by early 1945, as Japanese strategic planners recognized that destroying the canal's locks would cripple American logistics between the Atlantic and Pacific theaters. Intelligence estimates suggested that successful attacks on the canal could render it unusable for up to 6 months, forcing American forces to route all supplies and reinforcements around South America, adding weeks to transit times and straining logistics networks beyond their limits. Dry runs conducted on wooden models of the canal's got-in locks demonstrated the feasibility of the attack plan, with pilots practicing precision bombing techniques against replica targets. The 3 completed I-400 class submarines represented only a fraction of the originally planned fleet. Japanese naval architects had designed specifications for 18 of these massive underwater aircraft carriers, enough to conduct simultaneous attacks against multiple targets across the Pacific and along American coastlines. Each submarine would carry 3 aircraft, providing a total of 54 planes capable of striking targets thousands of miles from their launch points. The scale of destruction these vessels could have inflicted, had they been completed and deployed earlier in the war, would have fundamentally altered the strategic balance of the Pacific conflict. American engineers examining the I-400's construction found evidence of manufacturing techniques and materials science that exceeded their expectations of Japanese industrial capability. The submarine's hull employed a unique figure-8 cross-section that provided exceptional strength while accommodating the aircraft hangar along the center line. This design required sophisticated understanding of structural engineering and hydrodynamics, solved through innovative approaches that American submarine designers had not considered. The pressure hull could withstand diving depths that exceeded the operational limits of most American submarines, while maintaining the structural integrity necessary to support aircraft operations on the surface. The propulsion system demonstrated similar technological sophistication, with 4 1,680-kilowatt diesel engines providing surface power and electric motors for submerged operations. The fuel capacity exceeded 1.75 million gallons, stored in tanks distributed throughout the hull to maintain proper trim during extended operations. Advanced air purification systems allowed the submarine to remain submerged for extended periods, with its large crew of 144 officers and enlisted men, while sophisticated navigation equipment enabled precise positioning for aircraft launch operations anywhere in the world's oceans. As American intelligence officers compiled their reports on the captured A-400-class submarines, they realized they had discovered not just an advanced weapon system, but evidence of Japanese strategic thinking that had anticipated future developments in naval warfare by decades. The concept of submarine-launched aircraft operations would not be seriously pursued by other navies until the development of ballistic missile submarines in the 1960s. Yet Japanese engineers had solved the fundamental technical challenges in 1943 and 1944. The underwater aircraft carrier represented a revolution in naval architecture that could have changed the entire nature of maritime warfare, had the war continued long enough for these weapons to be deployed effectively. The boarding party's flashlights cut through the darkness of the submarine's interior, revealing engineering marvels that challenged every assumption about Japanese industrial capabilities during the war's final phase. Chief Petty Officer William Hayes led the American inspection team deeper into the vessel's bowels, documenting systems that appeared decades ahead of their time. The electrical distribution network employed automated switching mechanisms that eliminated the need for manual breaker operations during emergency diving procedures. Ballast tank controls integrated hydraulic assist systems that reduced crew workload during rapid submersion sequences. The life support systems demonstrated sophistication that exceeded anything found aboard American submarines of comparable size. Air purification equipment employed multiple filtration stages, including activated charcoal scrubbers and chemical oxygen generators that could sustain the crew of 144 men during extended underwater operations lasting weeks rather than days. The galley facilities included refrigeration systems capable of preserving fresh food for month-long patrols, while freshwater production equipment could convert seawater to potable water at rates sufficient for the entire crew. Navigation equipment discovered in the control room represented the pinnacle of Japanese maritime technology development. The submarine carried multiple gyro compasses with automatic correction systems that maintained precise heading information regardless of magnetic interference or violent maneuvering. Radio direction finding equipment operated across frequency ranges that encompassed both military and commercial broadcast bands, enabling the submarine to navigate using terrestrial radio beacons across vast ocean distances. Depth measuring equipment provided precise bottom readings to depths exceeding 1,000 fathoms, essential for operations in the deep Pacific basins between Japan and the American coastline. The torpedo room forward of the aircraft hangar contained launch tubes of standard diameter, but equipped with advanced fire control systems that integrated target tracking with automatic torpedo guidance. 8 tubes provided substantial firepower for conventional submarine warfare, while torpedo storage racks held additional weapons that could be loaded rapidly during surface operations. The torpedo loading mechanisms employed pneumatic assist systems that reduced the physical effort required by crew members, enabling faster reload times during combat situations. Perhaps most remarkably, American engineers discovered that the I-40's designers had solved fundamental problems of submarine aircraft operations that would not be seriously addressed by other navies for another 2 decades. The aircraft recovery system included a specialized crane capable of lifting damaged aircraft from the water and returning them to the hangar for repairs during extended patrols. Spare parts storage compartments contained complete sets of replacement components for the Siren aircraft, including propellers, control surfaces, and engine components. Maintenance facilities within the submarine included machine tools capable of fabricating replacement parts for both aircraft and submarine systems. The fuel storage system demonstrated exceptional engineering that enabled the submarine's unprecedented range capabilities. Multiple fuel tanks distributed throughout the hull maintained proper trim during consumption, while fuel transfer systems could move thousands of gallons between tanks to compensate for changing weight distributions as supplies were consumed. Fuel purification equipment removed water contamination and sediment that accumulated during extended storage, ensuring engine reliability throughout multi-month patrols. Reserve fuel tanks provided emergency supplies that could extend patrol duration beyond the already impressive baseline endurance. As American intelligence officers compiled detailed reports on their findings, they began to understand the full scope of Japanese strategic planning that had motivated the I-400 program. Captured documents revealed target folders containing detailed intelligence on American coastal installations, with particular emphasis on naval bases and industrial facilities along the eastern seaboard. New York Harbor had been mapped extensively, with approach routes planned to avoid known patrol areas and defensive installations. Washington, D.C. target folders included detailed photographs of government buildings and military installations that could be struck by aircraft launched from submarines operating off the Virginia coast. The Panama Canal attack plans proved even more sophisticated than initial interrogations had revealed. Japanese intelligence had conducted extensive reconnaissance of the canal's lock systems, identifying critical structural points where explosive damage could render the entire waterway inoperable. Tidal charts and weather patterns had been analyzed to determine optimal attack timing that would maximize both aircraft performance and target vulnerability. Alternative escape routes had been planned for surviving aircraft, including potential landings at airfields in neutral countries or controlled water ditching in areas where crew recovery might be possible. Intelligence estimates captured aboard the I-400 suggested that successful attacks on the canal could disrupt Allied logistics for periods extending well beyond the 6 months initially calculated by American planners. The Japanese had identified secondary targets within the canal zone that could be struck simultaneously, including power generation facilities and freshwater pumping stations that supported lock operations. Destruction of these supporting systems could extend repair time significantly, potentially crippling Allied supply lines between the Atlantic and the Pacific theaters for the remainder of the war. The biological warfare documentation discovered aboard the submarine revealed planning for operations that would have constituted unprecedented attacks on civilian populations. Operation Cherry Blossoms at night called for aircraft launched from the 400-class submarines to disperse plague-infected fleas over major California cities, including Los Angeles, San Francisco, and San Diego. The timing had been carefully calculated to coincide with weather patterns that would maximize pathogen dispersal while minimizing the risk to attacking aircraft. Ground teams carried aboard the submarines would have landed at isolated coastal points to establish additional biological warfare distribution points inland. The sophistication of the biological warfare planning demonstrated coordination between the submarine program and Japan's most advanced research facilities. Unit 731 had developed specialized bomb casings designed to burst at optimal altitudes for pathogen dispersal while maintaining organism viability during the flight from submarine to target. Weather analysis had identified seasonal patterns that would enhance disease transmission among urban populations, while intelligence networks had mapped population density patterns to maximize casualty projections. American medical officers reviewing the captured biological warfare plans expressed shock at both the technical sophistication and the potential civilian casualties such attacks could have inflicted. The plague-infected flea bombs had been tested extensively in occupied China, where they had demonstrated devastating effectiveness against unprotected populations. Casualty projections for attacks on California cities suggested that hundreds of thousands of civilians could have been killed or infected, with disease transmission continuing for months after the initial attack. The timing of Japan's surrender had prevented the implementation of Operation Cherry Blossoms at night by mere weeks, as the planned attack date of September 22, 1945, approached rapidly when Emperor Hirohito announced Japan's capitulation on August 15th. American intelligence officers calculated that the I-400 submarines had possessed sufficient time to complete their approach to California waters and conduct the planned biological warfare attacks if the war had continued beyond mid-August. The captured documentation also revealed the extent to which Japanese naval planners had anticipated American countermeasures against submarine aircraft carriers. Alternative launch procedures had been developed for operations in areas with heavy air patrol coverage, including night launches timed to exploit gaps in radar coverage patterns. Aircraft recovery procedures included contingencies for situations where submarines might be forced to submerge rapidly, abandoning aircraft that could not be retrieved quickly enough to avoid detection. Japanese engineers had even considered the possibility of American forces capturing intact I-400 submarines and had incorporated self-destruction systems designed to prevent enemy exploitation of the advanced technology. Explosive charges had been positioned throughout critical systems, including the aircraft handling equipment and navigation systems. These charges could be detonated by the commanding officer using controls located in the conning tower, ensuring that sensitive technology would not fall into enemy hands, even if the submarine itself was captured. The crew training programs for I-400 operations had required years of specialized instruction that reflected the complexity of submarine aircraft carrier operations. Pilots underwent extensive training in aircraft folding and unfolding procedures, while submarine crews learned aircraft handling techniques that differed substantially from conventional submarine operations. Launch and recovery procedures required precise coordination between submarine and aircraft crews, with timing measured in seconds rather than minutes to minimize surface exposure during operations. Navigation training for I-400 crews included celestial navigation techniques that enabled precise positioning anywhere in the world's oceans, without reliance on radio navigation aids that might reveal the submarine's location to enemy direction-finding equipment. Weather prediction training enabled crews to identify optimal conditions for aircraft operations, while communications training included procedures for coordination with aircraft during extended missions far from the launching submarine. The maintenance requirements for I-400 operations exceeded those of any previous submarine class, requiring crew members with specialized training in both submarine and aircraft systems. Engine maintenance crews underwent training on both submarine diesel engines and aircraft power plants, while electrical technicians learned to maintain both submarine and aircraft electrical systems. The complexity of maintaining two entirely different types of military equipment aboard a single vessel had required the development of new training programs and maintenance procedures. As American engineers completed their exhaustive examination of the captured I-400 submarines, they reached sobering conclusions about the potential impact these vessels might have had on the Pacific War's outcome if they had been deployed earlier and in greater numbers. The strategic implications extended far beyond the immediate threat to American coastal cities or the Panama Canal. The I-400 class represented a fundamental shift in naval warfare that could have rendered traditional concepts of oceanic distance and coastal defense obsolete. The examination revealed engineering principles that would influence submarine design for decades to come. The I-400's revolutionary hull configuration distributed structural loads through innovative internal framework systems that enabled the massive vessel to withstand crushing deep-water pressures while maintaining the structural integrity necessary for surface aircraft operations. American naval architects studying the design found solutions to problems they had not yet encountered in their own submarine development programs. The ballast system employed automated controls that reduced diving time to levels comparable with much smaller submarines, despite the I-400's enormous displacement. Sophisticated trim systems maintained precise underwater stability, regardless of aircraft loading configurations or fuel consumption patterns. Emergency blow systems could surface the submarine from maximum depth in emergency situations, a capability that required enormous compressed air reserves and specialized valve arrangements throughout the pressure hull. The crew quarters reflected Japanese understanding that extended patrol operations required living conditions superior to those found aboard conventional submarines. Individual bunks replaced the hot bunking arrangements common in smaller vessels, while recreational facilities included spaces for off-duty activities during month-long patrols. Medical facilities included surgical equipment and pharmaceutical supplies sufficient for treating serious injuries or illnesses without returning to port. Communication systems discovered aboard the I-400 included long-range radio equipment capable of maintaining contact with fleet headquarters across Pacific distances. Direction-finding equipment enabled navigation using distant radio beacons, while radio intercept capabilities allowed monitoring of American naval communications. Encryption equipment protected sensitive communications from interception, using codes that American cryptographers would spend months attempting to break. The ventilation systems required for aircraft operations presented unique engineering challenges that Japanese designers had solved through innovative approaches. Air circulation during surface operations had to accommodate aircraft engine exhaust while maintaining breathable atmosphere for crew members. Emergency ventilation systems could clear dangerous fumes rapidly during aircraft maintenance operations or fuel handling procedures. Air purification during submerged operations removed carbon dioxide and other contaminants generated by the large crew complement. Storage compartments throughout the submarine contained supplies for extended independent operations lasting months without resupply. Food storage included refrigerated compartments for fresh provisions and dry storage for preserved foods. Spare parts inventories covered both submarine and aircraft systems, enabling repairs of complex equipment far from port facilities. Tool storage included specialized equipment for aircraft maintenance and submarine repairs. The machine shop facilities discovered within the submarine astonished American engineers who had never seen such comprehensive manufacturing capabilities aboard any naval vessel. Lathes and milling machines enabled fabrication of replacement parts for both submarine and aircraft systems. Welding equipment provided repair capabilities for structural damage, while electrical repair facilities included equipment for rewinding motors and generators. These facilities enabled the submarine to operate independently for extended periods without external support. The fate of the I-400 class submarines was sealed not by enemy action, but by the emerging tensions of a new conflict already brewing between former allies. As American intelligence officers completed their exhaustive documentation and the Soviet Union demanded access to examine these revolutionary vessels under post-war agreements, the United States made a decisive choice. Rather than share technology that could reshape naval warfare for decades to come, all three I-400 submarines were transported to Pearl Harbor for final evaluation before being deliberately scuttled off the coast of Oahu in 1946. The I-400 and I-401 met their end as target practice vessels, struck by torpedoes from American submarines on May 31st and June 4th, 1946, respectively. They sank to depths exceeding 2,000 feet, taking with them the secrets of underwater aircraft carrier operations that would not be seriously pursued again until ballistic missile submarines emerged in the 1960s. The Cold War had begun even before the Pacific War's ashes had cooled, and America chose to bury these technological marvels rather than risk their revolutionary concepts falling into Soviet hands. For nearly 60 years, the I-400 class submarines rested in their deep Pacific graves, their existence known only through classified American intelligence reports and the fading memories of engineers who had examined them. Not until 2005 did the Hawaii Undersea Research Laboratory finally locate the wrecks, finding them remarkably preserved in the cold depths, their massive hulls and sophisticated systems still intact enough to confirm the extraordinary nature of what Japanese engineers had achieved in the final desperate years of the war. The discovery of the I-400 submarines represented more than just the capture of advanced enemy equipment. It revealed the extent to which Japanese strategic thinking had evolved beyond conventional naval warfare concepts, anticipating developments that would not appear in other navies for another generation. These underwater aircraft carriers embodied Japan's final attempt to leverage technological innovation against overwhelming material disadvantage, to strike decisive blows against an enemy whose industrial capacity had proven impossible to match through conventional means. Yet for all their technological sophistication, the I-400 submarines arrived too late to alter the war's outcome. Japan's industrial collapse, fuel shortages, and the relentless advance of Allied forces had rendered even the most brilliant innovations strategically irrelevant. The submarines that could circumnavigate the globe found themselves confined to increasingly restricted waters as American forces closed in on the Japanese homeland. The aircraft designed to strike New York and Washington instead prepared for desperate attacks on Allied bases in the Pacific, missions that would be canceled by Japan's surrender before they could be attempted. The I-400 program stands as testament to human ingenuity applied under the most desperate circumstances, engineering excellence achieved despite impossible constraints, and strategic vision that transcended the immediate limitations of wartime reality. American engineers who examined these vessels called them the most incredible machines that never fought, marvels of technology that represented what might have been possible if they had emerged earlier in the conflict when Japan still possessed the resources and strategic position to employ them effectively. In the end, the I-400 class submarines were superweapons built to change history that instead sank beneath it, their revolutionary concepts lost to the depths until researchers decades later would rediscover them and marvel at what Japanese engineers had accomplished in those final, desperate months of the Pacific War.